If terminal voltage is 5.8 volt, then what is the resistance of external circuit? Here given circuit, uh, the EMF of cell is 6 volt and internal resistance R equal to 1 ohm, and terminal voltage is given 5.8 volts. So we can use V equal to E minus IR, or IR equals to E minus V, or I equal to E minus V by R. So here EMF is given 6 volt, 6 minus, and terminal voltage 5.8 volt, 5.8 by internal resistance is 0.2 ampere. So current in the circuit is 0.2 ampere. Again V equal to IR, this implies R equals to V by I. So 5.8 by 0.2 equal to 29 ohm. So the external resistance is of 29 ohm. Next, the potential difference between the terminals of a 6 volt battery is 7.2 volt. When it is being charged by a current of 2 ampere, what is the internal resistance of the battery? Here EMF is given 7.2 volt and terminal voltage is 6 volt, and it is being charged by a current 2 ampere. What is the internal resistance? Then we have to calculate the internal resistance. The situation is shown here. In the cell is in charging condition, and the EMF of cell is given, and also terminal voltage is given. So we know that in case of charging, V equals to terminal voltage equal to EMF plus I into R. This implies V minus E equal to IR, hence R equals to V minus E by I. So 7.2 minus 6 by 2 equal to 1.2 by 2, 0.6 ohm. Answer. Next, the internal resistance of an accumulator's battery of EMF 6 volt is 10 ohm when it is fully discharged. As the battery gets charged up, its internal resistance decreases to 1 ohm. The battery in its completely discharged state is connected to a charger which maintains a constant potential difference of 9 volt. Find the current through the battery A just after the connections are made, and B after a long time when it is completely charged. Solution: just after the connection given VA minus VB, this is the here shown charging source is added, and cell is being charged by a charging source of 9 volt. Given VA minus VB equal to V, the terminal voltage is given 9 volt, and EMF battery is 6 volt and R equal to 10 ohm. Now V equal to E plus IR, hence I equal to V minus E by R equals to 9.6 by 10 equal to 3 by 10 ampere, or 0.3 ampere after just being charged. Now after a long time, the internal resistance of cell become 1 ohm. So, and E equal to 6 volt. So I equal to B minus E by R equal to 9.6 by 1 equal to 3 ampere. So after a long time, the current through the current in the circuit will be 3 ampere. Next topic. For n identical cells in series, we have I equal to Ne divided by R plus Nr. Now case 1, if external resistance R is very small than N into R, that is total number to internal resistance, then I equals to E by I equivalent to E by R. This is the thus this is the current in the resistor due to only one cell, and if this is the current due to resistor due to only one cell. Therefore, series grouping of cells in such a case when external resistance is very small in comparison to internal resistance is of no use, because there is no use to add several identical cells, because current we gains finds in the circuit is equal to the single cell, equivalent to the single cell in this case. Now, if external resistance is very greater than a total number of internal resistance, that is R is very greater than NR, in this case I max is N into E by R. This time the current in resistor R is N times the current due to one cells. Therefore, series grouping of cells in this case is useful. Here in this case, when R is that external resistance is very large, then we get current N times of the single current. So in this case we get maximum current, and so this is the this grouping is helpful. Next, parallel grouping. For a battery of n identical cells, all are right connected. For a battery of n identical cells, all are rightly connected. So equivalent here it is shown the situation. Here all cells are connected. All terminals of positive terminals of all cell is connected to one point and negative terminals to another point, and this is called right grouping. All cells are in right grouping because all cells are in discharging condition, and it is external resistance. Now if we replace this whole cell with a single cell of E and resistance R by N, and this will be the equivalent resistance to this whole arrangement. So equivalent EMF will be E equivalent equal to E, and R equivalent and equivalent resistance will be R equivalent R by N plus R by N plus R. Hence I will be E equivalent by R equivalent, or I equal to E by R plus R by N. R by N. I equals to E by R plus R by N. Now case 1, if R is very that is external resistance greater than R by N, then I equals to E by R. This is the current in the resistor due to only one cell, and this is the case in which the current is due to only one cell. Therefore, such grouping of cell is of no use. So in this case, such type of grouping is not useful. So for example, if R is very greater than R by N, or I equals to E by R, this is the current in the resistor due to only one cell. Therefore, such grouping of cell is no use. Now if R is that is external resistance is very less than R by N, so I max is equal to N epsilon by R, and this time the current in resistor R is N times the current due to one cell. In such a case, parallel grouping of cell is useful. that is when external resistance is less than R by N, then parallel grouping is useful for us. B. Battery having cells of different EMF. Case 1. Two cells are rightly connected. Both the cells deliver current in same sense. Then we have to do it from figure. Here it is shown. This is cell 1 and this is cell 2. And both are connected in the same sense. That is, positive terminals of both cells is connected to one point and negative terminals to one point. And now current from cell 1 is I1 and current from cell second cell is I2. So we can write I equal to I1 plus I2 here at point P. So for first cell, VB1 minus VB2, that is potential difference between these 2 points. For if we see this circuit only, then VB1 minus VB2 equals to E1 minus I1 R1 or VB1 minus VB2 is equal to VB minus VC equal to V. So V equals to E1 minus I1 R1 VB1 minus VB2 equal to VA minus VC equal to V. That is terminal voltage. It is equivalent to terminal voltage. So V equals to E1 minus I1 R1. Hence I1 equals to E1 minus V by R1. V by R1 and equals to E1 by R1 minus V by R1. Equation 2. Now for the second cell, if we see from this cell, then VB1 minus VB2 will be E2 minus R2, IR2. So VB1 minus VB2 E2 minus I2 R2, or V equal to E2 minus I2 R2, or I2 equal to E2 minus V by R2, or I2 equal to E2 by R2 minus V by R2. This is the equation 3. Using 2 and 3 in 1, in this equation we get I equals to E1 by R1 minus V by R1 plus E2 by R2 minus V by R2. E2 by R2 minus V by R2, or E1 by R1 equals to E1 by R1 plus E2 by R2, a minus of V into 1 by R1 plus 1 by R2. Or this implies V equals to R1 plus R2 into R1 into R2 equals to E1 by R1 plus E2 by R2. This is equation I1. Hence V equals to E1 R2 plus E2 R1 by R1 into R2 by V equals to E1 by R1 plus E2 by R2 minus I, or hence V equal to E1 R2 plus E2 R1 by R1 into R2 minus I by R1 plus R2 into divided by R1 into R2, or equals to E1 R2 plus E2 R1 by R1 plus R2 minus of I into R1 R2 by R1 plus R2. Now consider both cell is replaced by a cell of EMF E equivalent and internal resistance R equivalent in between the points B1 and B2, and same current I is flowing through the cell. Then we can, from figure 2 we can write here, from figure 2 we can write VB1 minus VB2 equals to E equivalent minus I into R equivalent. This is VB1 minus VB2 equal to VA minus VC to E equivalent minus I into R equivalent, or V equals to E equivalent minus I into R equivalent. Comparing A and B, equation A and B, we have E equivalent equal to E1 R2 plus E2 R1 by R1 plus R2 equals to E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. This is question 6. And R equivalent as R1 into R2 by R1 plus R2 or equals to 1 by R1, 1 by R1 plus 1 by R2, or this imply 1 by R1 plus 1 by R2 equal to 1 by R equivalent. Now equation 5. Now equation 4 can also be written as E equivalent equal to E1 by R1 plus E2 by R2 by 1 by R equivalent, or into E1 by R1 plus E2 by R2 into R equivalent, or E equivalent by R equivalent equals to E1 by R1 plus E2 by R2. This is equation 6. Thus, in parallel combination, the equivalent cell has an EMF equal to E1 R2 plus E2 R1 by R1 plus R2, and resistance, equivalent resistance equal to R equivalent equal to R1 into R2 by R1 plus R2. Now if there are n cells of EMF E1 and E2 dash 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 En and of internal resistance R1 and R2 dash dash Rn replace respectively connected in parallel, then EMF and internal resistance of equivalent cell is given by E equivalent by R equivalent E1 by R1 plus E2 by R2 plus dash dash En by Rn, and 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus dash 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 1 by Rn. In the circuit shown in figure, E1 equal to 3 volt, E2 equal to 2 volt, and E3 equal to 1 volt, and R1, R2, R3 equal to 1 ohm. It is internal resistance given. Find the potential difference between point A and B and current through each branch shown. Solution: we know that this is in parallel grouping. Parallel right grouping, so we can write 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3, or equals to 3. Hence R equivalent will be 1 by 3 ohm. Now again E equivalent is given by E1 by R1 plus E2 by R2 plus E3 by R3 into R equivalent. So 3 by 1 plus 2 by 1 plus 1 by 1 into 1 by 3 equal to 6 by 3 equal to 2 volt. Answer. As the equivalent circuit is in open circuit, hence VA minus VB equals to E equivalent equal to 2 volt and I equals to 0. Now as current is flowing in each cell, so they are considered to be in closed circuit individually. Now for first cell, VA minus VB equal to E1 minus I1 into R1. This implies I1 equal to E1 minus VA minus VB by R1 equal to 3 minus 2 by 1 equal to 1 ampere. And for second cell, VA minus VB equal to E2 minus I2 into R2, or I2 equal to E2 minus VA minus VB by R2 equals 2 minus 2 by 1 equal to 0. For third cell, VA minus VB equal to E3 minus I3 into R3, or I3 equal to E3 minus VA minus VB by R3, or 1 minus 2 by 1 equal to minus 1 ampere. Negative sign indicates current flow opposite to the assumed direction. Thus in this problem we said there is no current in the external resistance, and current is in the circuit is in the same circuit. Next one, find A. The current in the circuit. B. The potential drop across the 5 ohm resistor. C. The potential drop across 10 ohm resistor in the given figure. This is figure 1, this is figure 2.